Hey, how's it going? Yeah. Probably to show it off. Oh, for a second I thought that was a piece of yarn.
No, this is not. So that's who charges me.
I'll charge her my bag if you need it.
Do you really?
Yeah.
Oh my God. Can I just, it's fine.
Okay.
Should be good. Yeah. I'm just at 6%, and I know that once I hit 60, it just. Even more.
I think already. Yeah.
Sorry. Was I Young? Okay.
All right, let's get started. So it looks like we got a bunch of people online. We got a pretty full house here also. And, so this is kind of an interesting transition. We'll see how this goes. It's kind of flying without a net. And so up to now, we've had a lot of great material that's basically been presented by Yuri, the introductory material that, for the past few weeks. And, it's all, because we're professors and we like to present and share ideas and whatnot. But part of this also is that we're professors and we, I'd say the global royal we as a community, are researchers. And part of what we're doing also is understanding what other people have done and what advances are being made and whatnot. And so part of that, the whole goal of these initial introductory lectures from Yuri was to get to a point where we could start reading papers together as a group. And so this is the first step along that path and basically focusing on this paper. And I'm not projecting for some reason.
I mean, so you're not connected to the
I'm not connected. Checking online. Getting the wrong input.
Here's the right one. Same one that I used. You want? Yeah, showing the same. Something. Try. Let's try to disconnect and reconnect like that. Okay.
I'm sorry, for those of you that are online, we're having just no issues right now. HDMI.
So.
Oh, there we go.
Yeah. It just.
Okay. Projecting onto the screen here. So, like I said, the transition from lecturing to we actually call it community building, and we've been talking about these various papers and whatnot. And this is going to be an interesting one in particular. This paper that we have on multi-key FHE for a number of reasons. The least of which is that our initial implementation work that we've been focusing on the lab is actually built off the protocols that were here. And back to that, then, who actually the guys, Michael and Amadou, you met him in the meeting last week.
Yep.
Is for all intents and purposes, a collaborator, research partner of ours, and helping us design at least the protocols for this crypto system. And I jokingly tease that we're kind of like his code monkeys, if nothing else. But we're getting these things working. And just to say, he wrote code about 10 years ago to implement AES once into grad school. And we're a little bit different in that regard. So this system is quite useful for us in particular because we're basically building the proxy encryption scheme based on top of this what we call multi-key FHE that we have here. And so, like before, where a lot of the work that we were doing, a lot of the lectures that we had were primarily Yuri lecturing, I really want to have this be as conversational as possible. And so I don't expect you to read like with the Talmud or the Dead Sea Scrolls or something like that. But I'd like to have at least some of you that, especially those of you that are my official students, put some, real effort to read these, understand them, and try to be conversant on the material that we have here. So we can start to identify, what was funny, what was interesting, what didn't really look so well, and check it out. And, we'll see how it goes. So just say that, who at least downloaded it and printed it out? Most of the room. Actually give it like a fairly close read. Most of it, the first couple sections. So just kind of dive into it a little bit, and I'll assume everyone in San Diego has their hand raised.
You downloaded that list?
Yes.
Okay.
I've been working through it. I'm on page 5 now.
So, there was two different versions of it. There was the shortened version, was presented, I forget exactly where it was presented. But also the extended version, which is more easy access to get online. And so, the stock STOC is the supposed threat theory of computing. It's one of these big name theoretical computer science venues that they have every year. And I had to send a paper there once, and it had code described in it. And so basically, I was told very politely that does not present papers related to implementation. So, I think it was kind of a mismatch on my part anyway. So like I said, NTRU and whatnot. So like I said, I want to have this be primarily conversational. And so for those of you that actually downloaded it and looked at it at least a little bit, initial thoughts on what happened. I mean, so one thing that's quite different about this is that since it's got a lot of interesting words in here, multi-computation. And surely multi-computation from the standard like MPC type frameworks, and I think this is for your understanding, we'll have to maybe have a couple MPC type papers, either of someone like a Shafi Goldwasser or something like that. But it's more MPC built on pulling more from encryption. So the high level intuition of this is that it's in some sense a little strange. And FHE was designed primarily with the context of outsourcing computation. Have some sort of data, you give it to someone else, and they run computations on that data. And it's like this kind of very different two-party type model where it's kind of like your data from your phone to a cloud, for example. MPC is a little bit different where, the canonical example is, Yuri, Gianna, and I, we each have information about our total salaries, for example. We have something that's called millionaire's problem. And I want to know who's basically got the highest salaries so we know who can buy coffee with each other. We don't want each other to know how much we actually make. And there's this protocol that was designed as, probably as initially as an intellectual exercise to figure this thing out. It's called the millionaire's problem. We'll get to some other time. There's these fairly standard protocols where we can, in some sense, encrypt data, do sort of joint computation on this encrypted data, and then we have some high degree of assurance that we can perform this computation and get a result out of this. This FHE is a little bit different in kind of regards, in that each of us take our own data and we can use, hypothetically a centralized server, like server. And the reason is that FHE falls apart in a sense for multi-party computation is that there usually has to be a common key. And so suppose using standard FHE, Gianna and I want to run joint computation. Well, shared public key, encrypt the data, and we give it to the cloud. We can run the computation and result, and then share the result to us. And then each decrypt the result with a secret key. Well, for example, you're in cahoots with Jeff Bezos.
I don't hear anymore. Kurt, Do you hear us?
I don't hear Kurt.
Our side. Still there? Hello? Is anybody?
Hello, there? All right, so, our wireless just went down.
Ah.
I'm connecting through my phone now.
Review morning and
It's recording.
It's recording, still recording.
So, much, I don't know.
No, I don't say anything, it immediately stops.
Yeah.
So,
All right, sorry about that. You missed anything. So like I said, I was gonna turn it to my, focus actually testing how. All right. Turn to the audience. It's my colleagues here or online. What struck you? What struck you as interesting in this paper? I mean, hopefully you basically saw the connection about one version of the paper to MPC and then some of the NTRU type stuff also. Look at it, and I've been staring at this stuff for about 4 years now, and it kind of just looks like it's like introductory physics at a certain level. So, somehow I kind of lost the amazement, but it's still pretty amazing, I think, to actually get it work. Initial comments on it?
First.
Yeah.
Obviously, I've read it a couple of times, so I'm used to this paper, used to seeing this paper now.
Yeah.
Do you have any comments? I mean, when you studying, I mean, your thoughts?
A little bit. Get to read as much of it as I would have liked. It was quite epic. I don't know, it's really neat. The back
Maybe data folks, maybe someone there wants to.
Yeah, I don't know if someone in San Diego wants to say anything about it.
Yeah, I thought it was interesting. You have, multiple keys that you can use to, but the NTRU system still holds up using multiple keys.
Right.
Yeah, and then a joint key to decrypt as well being used. That the fact that NTRU it looks like the similar construction as the construction that we saw last week. It seems like a robust scheme.
Yeah, one thing that actually kind of surprises me about crypto systems in general, that there's actually a relatively small number of crypto systems that are out there. I mean, there's VG, which is a variant of VV. There's NTRU-based schemes, and then other variants for like, for example, AES and RA and whatnot. And this NTRU is exactly right, that it has all these kind of really interesting properties to it. It's almost like it's too good to be true. Regards. I mean, there's been other crypto systems that have come up, things like for example, GSW is one to look at eventually also. This property about how, particularly this, into it, we'll actually pull it up on the screen. Encryption operation, we see right here, well, basically you're sampling these two levels of noise, SE, from sort of generator chi. And we have the ciphertext, which is in some sense you're the key, multiplying it by some noise, adding by some, some even amount of noise, and the message in. And this special property about how you're adding the key to the noise actually gives you these really nice properties. And maybe this is not something that really came across in some of the lecture last week. So let's actually look at this equation a little bit that I'm just highlighting right here. Let me actually zoom in on it, because I think this is really, really important.
Yeah, there are problems behind it.
Yeah. Let's see. And it's more me just trying to focus on intuition as much as anything right now. And so let's look at this, because one thing that Yuri was getting at quite a bit last week was when he was talking about these crypto systems. This is particularly, I think this is one that's customized for plain text polynomials that are
That's correct.
right. And so you got this message, and basically this error term, multiply, which means it's always even.
In the case of binary polynomial.
The kind of binary polynomial. And generalize this to, for example, plain text. So when I say binary polynomial, it's basically a plain text, which is a vector of zeros and ones. Right? And you can generalize that if you want to be a vector of things from 0 to p, or 0 to 1. Right? So actually, we'll get to this next week when I talk about VoIP and how we, set up the VoIP encryptor using how we took advantage of that. This key built by another set of noise. And if you can see basically the secret key, all these various encodings, the C is some bit of even noise, something that is for lack of a better term, mod key, right? And when you go look at the decryption step, and we'll turn to that in a second, and you look at the decryption step, you're basically what you're doing is you're, sorry, this is actually not a secret key, this is a public key. Sorry, and the public key is effectively reciprocal key. And this multiplication by the secret key.
Anyway, one polynomial just generated using this function divided by the, multiplied by the inverse of the secret key.
So
there's
yeah.
two polynomials involved in that.
Yeah, so basically it's, the inverse of the secret key. And so effectively what you're doing is that if the public key is the inverse of the secret, you can multiply by the private key, the secret key. And this term just basically falls away. Right? And this other noise, because it's all even, that effectively doing this decryption, because this extra noise is what we call even, all this other falls away when you basically perform this modulus operation and then decrypt also, which is the way this message term.
The mathematical interpretation of what's happening with the food. So there.
I'm sorry, is someone online?
Oh, no, you can proceed.
Sorry, yeah.
Yeah, so it's just mathematical. We talked briefly about it in the previous lecture. So is to be uniformly distributed. So that's the assumption that's made here. And the reason why it's uniformly distributed is because of I call it the NTRU problem. That's the first step. So according to the NTRU problem, so we have H defined as G multiplied by the inverse of private key F to the power of -1. And that result is believed to be uniform based on, I'll use the so-called NTRU problem. It's actually called differently. And the fact that H is considered as uniform, randomly uniform, we apply the first two terms with the second problem, ring LWE problem, which tells us that if you have as uniform and you use two polynomials S and E, the result of the summation of those two terms, HS plus 2E, is going to look uniform. So that tells us, again, uniformly distributed random. So I'll use the word random. And so basically what happens here is that the sum of the first two terms is random, and we're adding that random polynomial to the message itself, making the message look random in a sense. So that's the general idea. So it's based on those two problems, NTRU and ring LW. Ring LW is a much stronger problem.
Yeah.
Now, I mean,
You need to tell me. Yeah, no, this is a very, very good point. So this is, in some sense, the real gist of connecting things that we've been talking about the past couple of days, and how it connects to building this crypto system. And this is, in a sense, one of the cleanest, easiest to read papers in this regards, which is one of the reasons I chose it, because you could see this really kind of clean connection from what we're talking about here to things that actually start to work and you actually start to use. Even if, you might not be getting to the multi-key part of it, even if we just focus on the FHE components to it. For the time, it's probably a thing to do, just to start it. In some sense, even if we spend a couple weeks just on this one paper, I think time very, very well spent for our group in particular. And, I might have, poked a little bit to try to get you to read it closely over this week. Well, it takes a little time to just kind of internalize. But if there's one thing that we internalize over the next couple of weeks, having this one paper and understanding this one paper really, really well over the next couple of weeks is going to be really for all of us.
It's probably the most important paper at this moment, because the scheme that we're implementing is also indirectly embedded in that multi-party scheme that we have there. So
the pre-scheme that we've been talking, so a lot of us have been mumbling about to some extent with proxy re-encryption. Basically, that means is, do you know proxy re-encryption is? I'm sorry.
Yeah.
No, I do. I mean, maybe more people on that side of the room. When I say proxy encryption, does that mean something to you guys? It's okay. No. Okay, good. I'll describe it. Proxy re-encryption. So let's talk about my two closest guys right here. People. You're right. So he likes to hang out in the lab. right? In and out, Yuri goes in and out, but Jan is always there to give messages back between us. And so I might not coordinate with Yuri ahead of time. For example, take a message and I encrypt it. So pass it to Jan. And you would hold on to it, and Yuri comes in the lab, Jan could go get pass it to Yuri. This works really well if Yuri and I have a shared secret key. We don't coordinate, and we need to change it every day, or Cassie might show up later, or Osho guy, or Nair and Suganda. They're no one's in the lab anywhere near as much as Kiana, it seems like sometimes. And so this can be the central point, but we don't want Kiana to read everything because hey, we trust them totally. And so what we can do is that proxy encryption is a way of I may not share keys with everyone, but one can send me their public keys. And based on everyone's public key, getting standard, using a public key server or something like this, and something that we might actually build, hopefully very soon, much sooner rather than later, that use this scheme such that I can get Osho's public key. I can basically generate what's called a re-encryption key. I can key to Yana so that when I have a message, I encrypt it using my public key. And that this message will eventually have to go to Osho is to take my public key encryption, convert it with my key, use the encryption key to something be decrypted only by Osho. And full adversary, right? All of my communications and all the encryption keys that I might generate, he can cover any information I encrypt and any other encryption they might give to Osho or Rogai or Cassie or anyone else. And so, for operations, this is actually very important for a lot of information, even like a secure Twitter. This has also a lot of DoD type applications, pub sub applications. I publish a lot of information over time, and I might, Vino goes and publishes a paper like this, and he not know later who might go and need it. But for example, delegate access to Cassie, to Yuri, the good people over in San Diego, and we'll never get access to it. But then delegate access from things encrypted by Vinod to Osho, Rogai, to Cassie, whoever. This is what's called the proxy re-encryption scheme. Jan operating as my proxy is what's called re-encrypt information. And then right now, with this proxy, we almost have it working, is the scheme of this re-encryption. And so basically, to go and build a webinar framework, a pub-sub framework, and all these other kinds of nice things that can doing things like, for example, in civil society, things like that just want to go and share information. Journalists know who read their articles, but they want to get access to their articles. And even if the server that the articles are published on might be fully compromised later, everything and whatnot. And so we're kind of putting the pieces together. I know this is more high level right now, but this scheme that we're basically building on this multi-key FHE stuff, very NTRU, has nice properties, basically called proxy encryption to it also. This is what we're building right now. But anyway, bring it back to the mathematics of it. What we're doing. And a lot of it is built on this scheme right here, where we have this key gen. And key gen operation this is exactly what Yuri was presenting last week, or two weeks ago. Yeah. And generation of G. And chi is this discrete Gaussian distribution. And we'll talk in the beginning, and as you go through the papers, you'll see this a couple different ways and a couple different times. Elite crypto schemes, lattice crypto schemes, and this chi generator. And one thing I'll also say is that if you want to be my doctoral student, want to be my master's student, I get kind of wrapped up around stochastic measures, stochastic modeling, stuff like that. And this is, I'm going to encourage you to take maybe a class in the School of Mathematics to talk stochastic modeling. Hopefully I don't have to convince someone from an ECE type background. This stuff's really useful sometimes for doing signal processing. I think it's just fun anyway. I know Cassie likes to solve puzzles. These are my puzzles to an extent. But also, if you want to go to financial analytics, there's actually a lot of applications for Wall Street stuff too. You need another incentive, like a plan B if you don't want to do crypto later. But anyway, And so these generators, chi, originally were what they called uniforms.
Uniform. Yeah.
Yeah. And so really it was, generators over the range of 0 to q minus 1, and uniform distribution of any one generator.
And the NJIT use scheme is based on that.
It's the NJIT use scheme, and this was part of my mild profanity, a huge pain in the ass from implementation. So you had to have this random number generator that would have these distributions that would have a real lot of randomness in it. So a big problem with generating randomness, generating random number samples. So this is a really hard problem, wise, of generating random numbers. And so you have a computational device, and there might be what they call a random number seed that's in here. That, there's a big philosophical discussion about what is randomness. How do you generate randomness? Well, you probably talk about your graduate class, right? And graduate crypto class, probably talk about pseudo-random generators.
Yeah.
Of course, right? And so how do you take this true randomness and basically make it stretch out? And you're generating these very large 0 to Q generations. And cases, Q is on the order of a couple hundred bits, possibly. Well, it would be, more than just 32 bits, right? Maybe cases, but you run a randomness really, really fast. And there was this result, I believe it was actually from Tromer and Hiker, if I'm not mistaken. I think that was one of the authors of this. That they showed that, about the 90s, you have this uniform random number generator to generate very, very random numbers. You use these very tight, discrete Gaussian generators. And Keanu was just implementing them, or port from ones I had in MATLAB over to C++. And so effectively there was this discrete Gaussian with something, a parameter on the order of 6 was an overkill, which means you have a high probability of having 0, probability of negative 1 or 1 with probability of, say, like 20% of the time, negative 2, say, like 10% of the time, negative 3, say, like 5% of the time, and so forth. And so very, very small amount of randomness that you're generating that would be used for these sample-bounded polynomials for generating these keys. And that was just adequate for security in these cases, which would help when you start doing things like homomorphic encryption. We actually start manipulating the data. The whole point was that when you manipulate the data, we'll get that in a little bit, that just kind of grows over time. And then you very quickly get your noise bounds. And so as we go through and start analyzing these crypto schemes, what is the nature of randomness? How do we generate this randomness? And what are the engineering trade-offs that we get? And this is actually a little aside, and I think that might be kind of cool to focus on eventually, is actually go and generate randomness. And so I'm not necessarily on the inside in government, and maybe the guys in San Diego know this, or know I do. My understanding is that a lot of the ways that people generate randomness nowadays is that like a physical card that you put in a computer that has like this big honking power resistor. The term. It's like an ohm resistor, and generate basically entropy, heat generated by this resistor. Basic physical universal properties, and that heat measurement off the resistor as a way of generating random noise. And it only goes so fast and so well, but that's just how it works. So how you have these very kind of strange physical properties of like Maxwell's laws, but Newtonian physics. That doesn't filter into actually crypto systems.
So white noise is basically the term that's used to describe that.
Yeah, and white noise actually has to do with the power spectrum of the noise being generated, but that's, we'll let Gavin talk about that sometime also, because you probably talk about white noise and brown noise and yellow noise and all things. I'm going very far afield, actually. So anyway, bring it back then. So we have these issues of bounded polynomials where we use f prime in this from this chi. It's actually a chi. And this f, which is one of the keys, it's an odd, you basically multiplying it, make like the sample by 2 and adding 1 to guarantee basically that F is, for all intents and purposes, what you might call odd. Which back to what it says right there, F equals 1 mod 2. And then, and this thing that always bothered me about a lot of these papers, and educational cleanliness. You know, we'll do a little update about this sometimes. It mix PK to me, but the H, K also.
It's semantics. I mean, H is semantic connotation.
And so you see down here is this H. Well, what's H? Well, that's the public key. Well, you have a symbol for public key, but you also have this H right here. And one thing that always bothered me, and you're talking to me, I'm always going to get it confused, and I'm sorry, it's just my limitations. I'm not a demigod. So that's how it is.
Notation is between mathematician and cryptographer.
The story behind that, Mamadou, I actually don't know the story about how that came about.
Yeah, it's like this from cryptography. I mean, the side usually they use like one symbol, like one number, using two.
Right.
Also, feature between the public key and the private key, because we have the PK and PK.
Right.
Those are the two. Usually they use one symbol to represent, instead of PK, which is two symbols, they try to use one, like one symbol to represent a variable.
Right. I guess that's exactly how it is. Kind of like how mathematicians might use an I, and then electrical engineers use a J to represent, square root of -1. It's just, it's kind of the legacy that we have sometimes. So, Mamadou.
Yeah.
So just, anyone have anything? I know I've been kind of just for a while.
Of the same donors or same private keys in that case, with the zero instance if there's some overlap. And it's actually, that same idea that we use for the pre-scheme, and that idea made this particular scheme relatively efficient based on this paper. But I think it's closer to the end. It's something to watch out when you read the paper closer to the end. They discuss the realization technique, which based on its binary decomposition. In mind, that's one of the strong points of the paper.
Right.
So I know it's probably not to jump to the to the end of all of the paper, but it's definitely something to pay attention to when you are reading the paper.
So actually, let me just go down to it, just so we can take a look at preview of things to come, so we can see where we're working towards.
You can probably search for realization or something like this to make it.
Oh. No.
It's available, right?
Are the participants? Yeah.
Yes.
I was making sure. For some reason, my computer's just barfing.
Yeah, I see that. Are you using Windows or Linux?
Yes.
Okay, you're gonna blame to Windows.
Yeah, blame what operating system you have. I should just get a laptop and just run the good old Plan 9 or something like that. No Plan 9.
need to do an task or something, it's maybe the executable is still running there in the background. But the executable may still be there all the time, so that wouldn't show on the view. Yeah, that's very sure. Yeah,
I'm sorry, guys.
Yeah, just right click on the no, that's the way we have that.
Okay.
So we can
You
work
can
it
do
out.
Control Shift Escape. Control Shift Escape.
Control Shift Escape.
Yep, Control Shift Escape will come up with
I
that.
usually do it with control.
Sometimes some computers are,
That's not even.
yeah, that's off the tree.
Control, yeah, that's the test manager, yeah, you were there. So,
Yeah.
maybe it's not that simple.
I'll try going.
Can you
yeah.
present? Do you have it on your screen?
It's actually a different laptop.
Oh, okay.
Yeah,
If you hit your Windows key, go to the bottom and go to Run.
but I can just a second.
Okay.
Yeah, I would need to
Go to Run
Yeah, I'm there, right?
and the word
Oh, run. Okay.
Yeah.
No, it's on.
Just
I
kidding.
Yeah, my laptop.
I can bring my regular weapon, maybe just a second.
Yeah. All right, guys. So, if those of you that are online, my computer just totally barfed. Embarrassing.
I can do it quickly.
Okay. Does San Diego at least hear us?
Yep.
Okay. So I should just do it freestyle dance style or something like that. So Yuri was talking about this relinearization. No, you're good. You're good. I turn on the light so I can see the paper a little better. So the shorter version of the paper, I think it was like halfway down in, so I have in front of me, I can't search. Page 11?
Yeah, physics.
Great, okay, that translates to.
That's 21.
Okay.
29, okay, good, got it.
Yep.
We're going to go from hard copies here, right?
Okay, so we'll go.
Yeah. So this notion of relinearization, just read off of it, because I can. So the use of relinearization, a technique first introduced by Gresky and by Kudenathan, introduced a public evaluation key, EK, that will output the keygen algorithm. Every time we multiply ciphertexts that share a key FI, we use the evaluation key to ensure that we only need FI and not FI squared to decrypt the new ciphertext. There's two things. To decrypt the ciphertext C star, we only need to multiply it by one copy of each secret key, making decryption independent of the circuit used to produce C star. The second ensures that the size of the joint secret key need to decrypt depends only on the number of keys N and not the circuit C that was evaluated. So basically, this so Yuri is actually there's the scheme. This was page, first column of page 1229. I see flipping through it back there. So basically, what this is this is in some sense a specialization for this multi-key FHE type scheme. It takes this fairly generic, actually very special, but relatively generic encryption scheme, and this property, this multi-key FHE. And what it basically is that you have all this data coming from, it's sent from different sources. It gets put in this kind of common representation, and then decrypt it. Basically, everyone has to kick in their secret key in some regards. And so do this kind of round-robin approach to do that in implementation. Basically, as it says, use the key to ensure that we only need FI and not X squared to decrypt the new ciphertext. Where X squared is basically square the ciphertext. I don't know if you wanted to say anything more about that, Yuri, because I know it's something that you said.
Yeah, and I actually brought up, I'm sharing the screen right now,
Oh, yeah.
so you can use my.
You can drive.
Guys, can you see the screen?
No, don't think they're going to be able to see anything. So we'll just use the screen here.
I'm sharing right now.
Oh, are you?
Here, I have still audio. Do we still have audio?
There you go, people. Can you hear anything?
Yep, we hear and we see, yep.
All right, let me restart my computer. I give a hard restart.
Okay, so I could probably use.
Is its audio dropped again? Not hearing anything.
Can you hear us? Switch computers over to yours. We're sorry about this.
Yeah.
Okay. So,
Yes, let's go back to realization. And which page?
1229.
Oh, further down. Okay. Okay, so this is the technique. So can everyone see my screen?
Yep.
So actually, this idea of just a sec, let me go through this. You can see the screen. Speaking, so the idea is to decompose the ciphertext that we have into individual bits of the message, and that idea to use, and that's what's behind the realization, to form the operation of re-encryption, or in this case, multi encryption in an efficient manner. The reason this realization is very important in this particular case because it replaces all instances of when FI, so the polynomial corresponding to the private key, when we have the power of 2 or higher, in other words, quadratic or cubic, we perform a special mechanism of keeping only one instance of the private key polynomial in a certain, using this trick that's discussed here. And why is this so important? Because every time we perform multiplication by a polynomial, we immediately narrow down the power ranges of values that we can work with. Because remember, our constraint equations for the correctness, and the other one for security. So they actually how ranges the constraint works and depends on the number of polynomial multiplications that we have to support. Generally speaking, for every new layer, for every new step in the fully homomorphic encryption, or we need to perform one extra multiplication, and that this realization is to reduce the number of these applications so that effectively although we're going to a certain depth, the number of multiplication is reduced, and in other words, this particular scheme can support further number of layers. That's a general idea, and I think a different paper introduced this concept, but this is the first paper that applied it and showed the practical value of the technique. And the same technique, and this based on the decomposition into individuals, is used for our pre-scheme. And the main difference of our pre-scheme compared to what's discussed here is that we will only have also the depth of 1. So we'll have the actual encryption, then we'll have the re-encryption. encryption done again. So we can call it depth 2 or depth 1, depending on how we compute it, but we'll only, in the pre-scheme, we only perform this FHE step once after the actual encryption. So that's why we chose pre-scheme to begin with. That's, although it's based on the same mechanism we use for the FHE scheme, but it's the number of the depth that needs to be supported in this case is just the encryption itself and re-encryption. But this particular technique is extremely important when you want to support larger depth and keeping everything within the constraints for smaller depth. I mean, just simply speaking. So, in my opinion, this is one of the points of this paper. Of course, it's hard to go through all the math, so I strongly suggest that when you have time to go through those derivations, and we can talk a little bit more in detail next time, but it's definitely a very interesting technique and very useful technique. And it's using techniques like this we can make FHE practical. Just speaking, it's one of those tricks that's used here.
So maybe what we should do is, if you go back up to this third page, because we actually just talked about half of the basic NTRU scheme, which kind of set some context before. Down the bottom right there. 122.
Yeah, it's right there.
Yeah, we have this, unfortunately, the authors or whoever typeset this put half the crypto system on one page and half the crypto system on the next.
Yeah. So we've discussed encryption, key generation and encryption.
Key generation and encryption.
And now
the next key part, let's go to the encryption step, which is the next column on the next page. And so this operation, where this output mu is F times C, where F is the secret key and C is the ciphertext. And I'm talking about how you basically multiply by F, and F is this map here.
Everything's shown here.
Yeah, I talk. I should just point. Okay, I'm talking. So you have basically C, which is this encryption step. And so C is H is the public key times this error message times message right here. And the error times all mod Q. And it works. So what you basically have is defined up above, or F times H above is
this is a critical step, actually.
Yeah.
So H is congruent to 2 multiplied by G and multiplied by F taken to the power of -1. So F multiplied by its inverse is congruent to 1. So this transition is very important because
and so this is basically defined by how the public key is defined. So you have F times the public is equal to 2 times G. Look at it in front of you. And so you have this basically this operation where you have 2 times GS plus EF equals Z. And this is, in some sense, the key part right there. That you have 2 times this other thing right there. So you're guaranteed to have something given, which is the secret key by the message itself. A pop out there. And so you have this guarantee step right here, which is basically this is I think that has to do with the noise term, right? The noise term.
Yeah. So the idea this will be correct after we apply mod 2 operation. We never wrap around. If this is F multiplied by C is called a ciphertext error. If this ciphertext error wraps around Q, and actually in this case Q divided by 2, but in reality actually Q divided by 4, but that's a different story. So if this expression, for the mod 2 operation to be to be valid and correct, to give the correct result, we need to make sure that this expression does not wrap around Q, just simply speaking. Because if it does wrap around Q, odd will turn into even, and etc., and then we'll have obviously problems deciphering it. And to get that estimate, we look at the bounds for each of the polynomials. Use the same technique that was discussed in our previous lecture. and then we make sure that the maximum value, you remember we discussed pessimistic and optimistic scenarios, does not exceed Q divided by 2. If that's true, then only the last step of decryption is mod 2 operation. Anything multiplied by 2 will go to 0 mod 2, and all we have left is Fm mod 2, and from our definition, you remember F is defined as 2 divided by F prime plus 1. So from the definition, F mod 2 is congruent to 1. So Fm mod 2 becomes congruent to M mod 2, which we just recovered our syntax polynomial M.
Right. And since, this is actually, if you're going to just read one part of the paper really, really closely, it's this transition from, page 1221 to 12222 over there. It really talks about the high-level crypto system and kind of the intuition. And you go down here a little bit to this next paragraph. And what is the extension that goes? Okay, you have this regular homomorphic scheme. How do you keep track of that? And it's a definition of, okay, here's encryption C1, here's a C2, and then you perform the SAT operation, which is the homomorphic addition. We'll look at it. I want to get to that. And this homomorphic multiplication operation, we'll get to that down a little bit. And so your encryption of M1 and M2 and C2, and effectively decrypting C1 plus C2 and C2 and C2 done with this joint secret key at F2, and more probably two secret keys F1 and F2. And this is where, in some sense, where the linearization information starts to pop in a little bit and get those pieces connected. Theo,
Sure.
So that joint secret key is used to decrypt the ciphertext on the cloud, right, on the server, and the remaining ciphertext for each individual party that's take part of the computation, they would need their own secret key to decrypt the actual ciphertext out from the evaluation of that function. Am I mean that correctly?
Yeah, but each party will have their own private key. That's correct, but the actual but I think the initial statement that on server side decryption takes place, I wouldn't say that statement is accurate, because we're still performing on the ciphertext. We're not actually decrypting anything at the server side. But just speaking, yes, I mean everything except for that statement I think is correct.
So its key is composed of all of the secret keys of the participants in the joint computation. So all the other participants should not know those secret keys. They should only know their own secret key. Okay.
And this multiplication that's involved in this process is what's optimized in that realization step. So we will actually be dealing not with the private key polynomials, but with the bits in the coefficients of the private keys. And when the bits are repeated, you can compact the operation of multiplication using that technique, and this reduces the effective number of multiplications. So that it's related to that operation of multiplying the polynomials and obviously multiplying the keys. I mean, that's the main focus is of multiplying private keys. That's where the biggest benefit is.
Right. So I just last a little bit. We're getting close to a little past the bottom hour. And so this notion of, here the homomorphication operation occurs right here. You have the addition of these two different ciphertexts. In addition to the two different ciphertexts, implication by this joint secret key, those two secret keys. You put out the math, and this is just basic junior high algebra. You have junior high in the United States, some of it, not less in this world.
Middle school algebra in Russia.
It's kindergarten algebra for India or someplace else. we did it in middle school. So.
Right, same here.
Yeah. So, you know, this expansion, you substitute for C2, you know, basically runs through the algebra. And you have the expansion basically on the error terms, the error terms, multiplied by the joint key. And you have this kind of middle term of F2, G1, S plus 1, S2. And the product, the joint key times the sum of the messages. And if you have this kind of this error term right there, this, you know, product error term right there is kind of fuzz factor error term, where this noise is rather small to this amount of noise. Kind of what's going on. And then you have this summation with this product term times the sum over there. And, you know, this looks a lot like the original encryption step. So the kind of proof kind of follows there. At least for correctness, if nothing else, not security.
Yeah, so we have two keys here, and you see that we have two polynomial multiplications, so three terms in the multiplication. Our analysis of the correctness constraint is based on number of multiplications. If we have one extra key, joint key, then obviously there will be 4 terms or 3 multiplications, and the basis of the analysis is how many can we support before we use special techniques such as bootstrapping. So that's the general idea. When you use multiple products by F1, F2, F3, etc., and try to somehow optimize it so that you do not lose much in constraints. I mean, at this particular step, so that you can go as many steps as possible. So that illustrates the general concept.
Right. A similar thing just down below, and I just want to kind of finish with that. Can you go down the page a little bit, Yuri? Sure.
That's why we have the constraint. So we need to set the parameters in such a way that it will not. So that's when you set up, when you develop those inequalities, that's basically what you control to make sure it doesn't. If it isn't, then, I mean, the overall product doesn't wrap around, then you're in good shape. A general idea.
A similar thing for this multiplication operation right here. Yeah, actually, in some sense, we're actually going through and reading papers about crypto systems. Generally, the homomorphisms in some sense are a lot hairier. And a lot of problems start off with noise management because noise grows exponentially with formations.
Yeah, so basically you have 4 terms in this case rather than three terms in the multiplication. So you add extra layers. So that's the problem.
You're multiplying polynomials. You have like a square of the number of terms effectively, and that's kind of what's going on here. That you have this product term of one noise term. You have this joint inner product right there. You have this error term times the messages, and they have essentially this thing that you actually care about at the end. And what they're doing is they're taking these first 3 lines, wrapped up with this 2 times some error term right there. You see the 2 is an equivalent of what is, and this key times a product of the 2 messages. That's how things kind of pop out. So you know, we had a couple hiccups with computer reviews and things like that. But you know, we could probably there's a lot going on in this paper, and I think we're going to focus on maybe a couple sessions on this thing in particular. Because it's a good paper for us to get our feet wet, get familiar with the notation, get familiar with the proof systems, that go into understanding these crypto systems. So I think, you know, really before I was making noise about just having this be, you know, one shot once a week kind of thing, I was actually rather foolish on my part, and it'd be benefit to us to actually kind of spend a couple of sessions on this. And so this is, you know, the reprieve for the folks here in Newark that you didn't read it before. Well, you know, you get the intuition of it now. Take a pass on it, and we'll take another dive on it next week. I'll be in San Diego. I'm going to be talking more about my work and the crypto system that I was building at BBN, and you know where that goes also. But also, and the week after that, we'll get back into this too. So
great paper. So we should. I mean, it's worth spending 30 seconds or 4 even sessions, in my opinion. That's a lot of those. I mean, it gives the foundation of how FHE schemes usually work and the pre-scheme also.
Yeah, and especially if we win this DARPA Safeware proposal, actually Vinod will be visiting here a couple of times most likely, so you guys can go and impress them with what your knowledge is. is seen, right? Yeah, there's, find an error, give a hard time with it. There's real firm data.
Actually, Q divided by 4 rather than Q divided by 2 is something that we discussed with him, a couple of weeks ago. So
yeah. People in San Diego, I owe you guys some email, but we'll just stay on the brown bag for now. Any comments, any questions? I know I've been kind of monopolizing time over this side.
At this point, looking forward to in some more depth in this paper.
No, thank you very much. Like I said, this is, probably more of just an introductory session for now. And like I said, we'll get down to maybe a couple of the proof systems and whatnot in the next week or two after our little sojourn, so to speak. Anything, comments from folks here in New York? All right, everyone, and sorry for the computer issues. So I should get dedicated just for this and have it be real stable and everything else. So thank you very much.
Thank you. Bye.
thank you.